So as I mentioned previously, compositional symbolic execution will allow us to compose symbolic execution with function specifications. So again, we're going to go through this by example. Now, we're going to need to, as I kind of mentioned, we're going to need to expand the result part into a symbolic state. So a symbolic state is going to have a couple of things. So we're going to have a variable store, which we're going to call hat s, and hat just means it's symbolic. So if you see hat anywhere, it's just a convention to mean it's symbolic. So this is our symbolic store. We're gonna have a heap as well, a symbolic heap. So a symbolic store just maps program variables, like the regular variables you use, to symbolic values, which, as I mentioned, are those kind of symbolic x's, and they can also be expressions of x and other things. For example, 2x is also a symbolic value. And then a heap just maps memory addresses to symbolic values, a symbolic heap. And we're also gonna, we're gonna have our path condition again, and that'll be hat pi. So those are the three components of our symbolic state. So I'm just gonna keep this here for reference. Yeah, the spacing is a bit off. Okay. So let's start with another function. So we're gonna have something very similar to what we'd had before. We're gonna have double in place. So I'm going to use Rust notation here, but obviously this applies to any language with pointers. So we're going to take a mutable reference to an integer, and it's gonna just mutate it in place. So in Rust, that would just be something like this. If I can type. Right, so we have the value of x is multiplied by 2. And so we're going to want to create a function summary for this, right? A specification. So let's first symbolically execute it so we know what the result is. So we're going to write down our symbolic state here for this function execution, to execute the body of the function. So we're going to have the variable, I should have actually named the variable. Yes, there we go. So our store is just going to hold the function parameters. So that's just going to be a mapping of variables to basically logical variables, which are commonly used in separation logic. Okay, so that's our variable store. You can imagine like the argument is a pointer to a heap allocated U32, for example. So we're gonna have a. Obviously, this doesn't have to be the case, but let's just keep things simple, and let's say that is the case. So we're gonna have a symbolic heap, which is gonna map x to some value v, let's say, right? So the address x is this pointer, and then if we dereference the pointer, we get a v, and we're multiplying that v essentially by 2. And as we saw before, this will only really work if we restrict the value of v to, well, U32 max divided by 2. So this should be a v. Yeah, let's do it like this. V is less than or equal to okay. So that's what we have here. So if we execute this, we're going to essentially, we only have one path here, right? Because we've already restricted the values of v to u32 max divided by 2. So if we do, again, our table of, we're not going to do path condition result. We already have the symbolic state, which includes both the kind of result and the path condition. So we're going to have the variable store doesn't change. We don't do anything there. Our heap does change. So we're going to need to map x to 2v this time. And our path condition doesn't change either. Okay, so this is our symbolic execution of this function body. And so what we can do is we can translate both the initial state and the final state into separation logic. So the initial state will be the function precondition, and the final state would be the postcondition of the function. So let's do that. So I'm going to put this in blue. So first we're going to map the parameters into logical variables. And sorry, these here should have been symbolic as well, because this is the symbolic state. Whereas in the separation logic specification, we're going to use regular logical variables. So this is our symbolic execution. And now this is our separation logic precondition. So first we just do a simple mapping of parameters into logical variables. Then we model our heap. Using, again, the logical variable. And we also model our path condition, which is kind of like a restriction of the values that we accept. Okay, and I'm going to space this out as well. So that's our precondition. Let me just check I've got this correct. Looks fine. Okay, and our post condition, well, we're just going to really take this final state here. And obviously at the end of a function, any local variables or parameters go out of scope, so we don't have to worry about that. So we can simply take this, and we're going to get rid of any parameters. We don't need this condition either, and we just need to remember that we have 2v at the end. Okay, so that's our function specification generated. So now that we have this, we can actually abstract away from the implementation of this function. So we're going to work with, we're just going to work with the function specification here. So we get rid of the body, we forget anything here. This is all we really have, right? This is our specification. So yeah, obviously there could be more code here. It doesn't have to be just one line. Obviously, this is actually a couple of operations because we have to load the value of x, so we have to do the doubling operation, and then we have to store the value of x again. So actually, it's a couple of operations, and we can just summarize that down to this function specification. Okay, so now we're going to want to actually execute this function, okay? So we're going to have some like other code here, and at some point in our program, we have, we execute this line of code. So we're going to take a starting symbolic state that is very similar to this one, and let's just actually make it a little bit bigger. Let's add more stuff to it. So let's just say we're going to have another variable. We're just going to have y maps to symbolic y, and let's just say we have another heap cell. Let's just say w, and also let's say that v is actually less than 10, or less than or equal to 10. And now, given the starting symbolic state, we're going to want to execute this function here using this function specification. So in compositional symbolic execution, there are two important operations, and those are consume and produce. So when we call a function, we're going to use consume to basically to consume the precondition and whatever state is necessary to execute the function. And then when the function returns, we're going to use produce to update our symbolic state. So we're not going to go into the function body at all. We're going to simply execute the function just by looking at the precondition and the postcondition. So we're going to need a couple of things for this consume operation. We need a mapping of essentially variables, of logical variables, the ones we have here in our function specification, to our symbolic variables over here, right? Because like I've used the same letter, but this could be anything, right? This could be 2x here. And then it would obviously, this x would map to 2x, right? It can be any symbolic value. So we're going to call this mapping theta. We can turn the color off. So theta is going to be a mapping. We're going to use substitution notation here. So we're going to say that hat x substitutes logical x. So that's going to be our mapping theta. And then we're also going to essentially, we're going to split our, oops, that's very thick. We're going to split our precondition into the arguments and the, like you could say, the real precondition here. So this is just a mapping of arguments, and this is the actual precondition. So the precondition, we're essentially just going to extract that, take all of that, and put it in here. And we're going to call that our precondition. And as I mentioned before, all of this is our symbolic state. So we're gonna denote the symbolic state with sigma hat. Okay, so that's going to be our symbolic state. So the consume operation is going to take our mapping theta. It's going to take our precondition. And it's going to take our symbolic state. Okay, so this is the signature of consume, and it returns something, I believe, I'm not sure what the proper LaTeX is for the arrow, so I'm just going to do a regular arrow, and that is going to return us some new mapping, and I'll get onto in a second what this new mapping is, and some new state. And this is actually going to be our state with all the state that the function uses. That state is going to be removed. So that's why it's called consume, because it consumes the state that is necessary for the function execution. So we're going to have some other sigma prime here. Okay, so what is consume going to do? So consume is going to look at our state, sigma, and it's going to pattern match it against the precondition P. Okay? And it's going to use theta for that, to kind of aid it in the pattern matching. And it's going to produce, well, anything that it pattern matched that was not already in theta is going to put it in theta, right? Because that's basically the result of our pattern matching. Pattern matching is basically mapping something to something else. So we're going to save the new mapping in theta. And sigma prime is just going to have the state that we pattern matched against removed. And more specifically, the heap state. So let's see what that looks like. So if we pattern match our state here, so we know that we're calling double in place of x, and x maps to symbolic x. So we pattern match, so we pattern match essentially this symbolic x to our logical x. So we've done the args part of the precondition. Now onto the actual precondition. Got a small typo here. We've got x maps to v. So we now pattern match that against our heap. We already know that x is symbolic x. So we look at that and then we find symbolic v. So that is something new. So let's make a note of that. So we're going to have theta prime, and that's just going to have what we already had essentially. So hat x substituting x, and now we're also going to have hat v substituting v. So that's our new mapping after the pattern matching. And we're also going to check our condition, right? Do we know for sure that v is less than u32 max divided by 2? Well, yes, we do, because we've pattern matched v against symbolic v, and we know symbolic v is less than or equal to 10. So that's fine. So we can consume it. The full kind of the full signature of consume is it can also return an error with some error message. So if, for example, this condition was not satisfied, like say for example v was unconstrained, symbolic v was unconstrained, then we would just get an abort with an error that we couldn't pattern match. And then we're going to have our remaining state. So we're going to have sigma hat sigma prime, and that's just going to be, well, we don't change the variable store because that's in another frame essentially. We don't have access to other frames, so we're just going to keep that as is. We are going to remove this thing from our state. We're going to remove x maps to v because we've consumed that. So we're just going to keep whatever's left. So we're just going to have y. And our path condition doesn't change either in this case. Okay, so that's basically the result of our consume operation. So now that we've done consume, we can do produce. So produce is going to take the post condition, which we're going to call Q here, and it's just going to be this essentially, right? Again, it's using logical variables, and we're going to need to, well, let's write the signature first. So produce takes in the post condition, it takes essentially the new mapping, and it takes the new state, right? The modified state here. And all it does is it gives us some new state. So what produce is going to do is it's going to take this mapping theta prime that we've produced over here, and it's going to essentially inject our post condition into our state sigma prime using theta. So this is very simple. We're just going to use theta to do this substitution here. I'm just going to copy this over. So we're going to take this and we're going to use theta prime to do a substitution. So it substitutes x to symbolic x and v to symbolic v. And there we go, we have our final state. So essentially, we were able to execute this function here solely by looking at the separation logic specification. We didn't need to actually execute the inner code of the function. And that is what allows for the compositionality and the scalability of compositional symbolic execution.